after estimating linear regression, the next thing is to perform diagnosis test. Now, to do that, we need the package called LM test. That will allow us to perform a series of diagnosis tests ranging from serial correlation to linearity test. So now, let me load LM test. You can see the code in line 14. This has been loaded. Now, I'm starting with W-Watson serial correlation test. Mind you, W-Watson serial correlation test can only detect first order serial correlation from the receivers. Now, let me run that. That's the function W test. So I use model here because the model is what I've used to store the result of linear regression model. So passing, you can say the p-value is significant. So this implies that there is first order serial correlation. Okay. Now let's check for a higher order serial correlation. Okay. So we can use BG test, that's Godfrey test. So although we can also use the Godfrey test for first order, but the only difference between BG test and the Watson is that BG can be used for to test for a higher order serial correlation. So let's compare the first order test from BG. You see, we have the same conclusion that the first order serial correlation test. But let's check for a higher serial correlation that is for lag up to 2. Let's check. So definitely, in this model, the errors in this model are serially correlated. You can see. Now, what of heteroscedasticity? So we use the form we want to carry out BPLM test. That's the Pagan test for heteroscedasticity. Here is the function. Yeah, BP test. Then we put in bracket model comma student size F. So then we run it. When we run it, you can see P is not significant, meaning that there is no heteroscedasticity. Okay. Now we can also test for residuals. And so we're going to test for normality of the residuals. How do you do that? We need a package called time series. That is T series. So let me load the package by running the code in 28. When we run the code in 28, then from there, now we want to extract residual from the estimated model. So the result of the residual we extracted, we want to store it as U at 2. You can see receipt, the function is receipt. The function are going to extract the residual receipt. Then model, that is the model we want to extract the residual of. Now, let's extract it. After extracting the residuals, yes, we will now apply Jackie-Beras test on the residual and see if the residuals are normally distributed. Here, you can see here that the result shows that residuals are normally distributed. Residuals are normally distributed. So far, our residuals are only serially correlated. Okay. Now let's check for linearity test by using Ramsey reset test for functional form. So here is the function reset. That is the function. So we use the model, the power. That is, we want to know whether it is non-linear. And maybe we have a variable that's raised to power 2 here. So now let's run it. If you run this, you can see it's not significant. It means that the model is linear. Now, what of structural change, or what we call parameter stability test? So how do we check that? So we need a package called structural change. Then we load the package using the code library in bracket structural change. Then let me load the library. Library has been loaded. Then we are going to use recursive custom test. Okay. So here is the function that is EFP. Then we write our formula. That is the dependent variable by the independent variable, then comma data we use. So we run that. After running that, so we now check for structural test. We can see, so we apply structural test on the custom. And you see, so when we apply it, so we are going to run that. You can see that it's not significant. It means our parameters are stable. no structural break. Then we can also plot the average figure and plot it. We can see this line is within the band. So it's not outside either of this red line. So meaning that our model is stable. Our model is stable. Now, if although there is no heteroscedasticity in this model, okay, heteroscedasticity and serial correlation are the major problems. Okay. Now, since there's no heteroscedasticity, I can ignore this one out. But for knowledge sake, in case you are doing an analysis and you discover heteroscedasticity, how do you correct for that? So the simplest way to correct for that is to use what is called heteroscedasticity consistent estimation of the covariance matrix. Okay, you can use it. That is white heteroscedasticity. We can use white heteroscedasticity consistent estimation for our uh, standard error. That we correct our standard error because when I say to strategy, our standard error will be underestimated. So if you apply this method, it's going to give us the correct standard error. Okay, because if standard errors are not correct, our t-test and therefore p-value will be wrong, and the inferences will be misleading. Okay, we may tend to say coefficients that are significant, they are not significant. Okay, now now, we want to check, we want to obtain the coefficient, okay, of the same model we have estimated before, but we want to use heteroscedastically consistent estimation. So here is the code, okay? Now, if I run that, I'm going to have the same estimate like I have when I run my original model here. Let's look at the summary here. It's the same thing you have here. But the only difference is that the the standard error has been corrected. You can see the standard error. The difference in standard, you can see standard error. This one standard error. Okay, meaning that it has been corrected, especially for the intercept. Okay, and for the learning rate. Okay, I think for the standard error of the data of LMS is not affected. Okay, you can see it that is not affected significantly. Okay, so by this, if my model is suffering from heteroscedasticity, although we don't need to correct for heteroscedasticity because based on our result, there's no heteroscedasticity issue. So we don't need to correct for that. In case there's a so we need to correct for that. Okay. Now, also, so the major problem we detect is that there is a serial correlation issue. Okay, in that way, if there's a serial correlation issue, what we are going to use heteroscedasticity and autocorrelation consistent estimation of our covariance matrix. Okay, this is similar to that of heteroscedasticity consistent estimation of the covariance. Okay, you can see here's the code. So we still obtain our coefficient. So here we are going to have this showing that we want to correct for that. So if we run that, let's see if we run that, so we are going to have this. So our standard has been corrected for, okay? You can see that. You can see that. So we can also run some other tests, although they are additional tests, okay? The additional tests, we can also run them like what we call a word test, uh, LM test, word test, and linear test, like test. So you can check, just read the code, you understand this when you read it. Okay, just read it very well. You can see what test. Okay.